Hello student, welcome to today's session. So today we are into the second session of organic series which we started yesterday, where I talked about the historical background and the definition of organic compounds in the session 1. So let me say the conclusion of last session, where we said that organic compounds are the compounds which are made up of carbon and hydrogen. Collectively they are said as hydrocarbons, and any derivative which we can generate from these hydrocarbons may also be classified under the category of organic compounds. So the objective of session 2, the objective of today's session would be to learn the chemical bonding required for the organic chemistry. Chemical bonding in itself is a very lengthy chapter, as and when I'm going to place this chapter in separately, we will be discussing it in length, but at this point of time we will be taking chemical bonding into consideration from the point of view of organic chemistry only. So this particular session may go in length, so stay, and after the session you feel quite strengthened with the topic of and another thing which I would want to place it, I'm not going to start with IUPAC naming or things like that. That I will take up somewhere after 4, 5, 7 lectures. So there you would see the intuitiveness or the off-beat unconventional way I am going to bring into the subject. And if in case you like this, and do use this hashtag as and when wherever you are studying, onto the comment section, and as per your wish. And one more thing, yesterday in the session 1 I spoke about this particular compound, which is benzene hexacarboxylic acid, which I named it as graphatic acid. Yesterday I may have written the spellings wrong, so please rectify this into your notes. Malatic acid, so the spelling was wrong. So let me write once again, because I love this particular compound very much, and we said about this thing that if we heat it, this water would go out, if you could recall, and one water from here, one water from here, so 3 water molecules goes out, and you end up getting something like this. And this particular compound may also be said as anhydride of malatic acid. What do I mean by anhydride? When you take out water out of something, we say it as anhydride. So this is anhydride of malatic acid. Yesterday, as you people know, maybe knowing it, that I record all of these sessions in one go, without sort of doing any sort of editing or things like that. So if in case some silly mistake or some fumbles come in during the session, please ignore it. And now let's start with the session. So as regard to the topic of chemical bonding, uh, organic compounds primarily be getting engaged with a type of bonding which we call it as covalent bonding. So what basically do I mean by covalent bonding? A bonding which take place because of the mutual sharing of electrons. When two atoms come close to each other and they mutually share their electrons to achieve the noble gas configuration, that type of bonding we commonly say it as covalent bonding. And primarily you would be seeing this covalent bonding in non-metals. Metals happens to undergo ionic sort of bonding, where there is formation of cation and anion. Here the covalent bonding is because of the mutual sharing. What does it mean? Now if I would say that hydrogen atomic number is 1, it is having 1 electron, and there is another hydrogen atom which is also having 1 electron. This electron I wrote in cross just to distinguish the electron from each other, but in a sense that both of these are same. Now this, in a way, this hydrogen is having atomic number 1, and the nearest noble gas to it is helium, whose atomic number is 2. So hydrogen would want to take one more electron to get the noble gas configuration. So by achieving noble gas configuration, this would become more stable. So what does it happen? So simply we would write it like this dot and this cross. This hydrogen, if I would say the hydrogen which I'm marking it with blue, this hydrogen take 1 electron of the hydrogen next to it, and the hydrogen, this which I have shown with the green marker, takes 1 electron of the other hydrogen, and thereby mutually sharing each other, they get the noble gas configuration. And this 2 electrons generally is being shown by this one line, or this is called a single bond. This is called a single bond, and we will be doing it in a bit of detail. So in the single bond, there is one electron coming from this side, let's say from A, and the other would come from the B. So in that way, this is called a single covalent bond. Now the question arises here, which is a very fundamental question, which happens to, because when you target some concept with a fundamentals, the things becomes very tough to address with. Now if I would say that, first let me say it like this, that who all are noble gases. So always remember, noble gases are helium 2, neon 10, argon 18, krypton 36, 54, and 86 radon. So if I would say what is the mobile number of noble gases, so I usually say in my physical classes 2, 10, 18, 36, 54, 86. This is the, these noble gases, you always have to remember it. Every element would want to achieve this configuration, and if in case you ask somebody why every element want to achieve this configuration, this question is a tough to address with, that why they all want to take the noble gas configuration. So, if I would say in simplicity that the by achieving the noble gas configuration, they tend to become more stable, or there are lot many aspects into it which can be addressed with, like exchange energy, symmetry, that we do study in the atomic structure. But at this point of time, you have to just say it with this assumption that every element want to acquire the noble gas configuration. If I would say it in a jolly way, that just like in a day, we always would want to be stable. And how could I be stable? That if I would take a good sleep. When we are in the sleeping mode, we are in the best state, in the sense that we are in the resting state. We are most stable. And similarly, you can say it that way, that while acquiring this much number of electrons, these elements tend to become in a stable mode, they tend to acquire. So in that sense, you can say it related with this. Otherwise, with the atomic structure, we can address this more effectively. But at this point of time, I'm not sharing it that way. Just here, take it an assumption that noble gases every element want to acquire the noble gas configuration. And strictly, if I would restrict myself to the organic chemistry, I'm more interested in these three: the first period in the periodic table, second period, and third period. So our story would run down to first, second, and third only. So if I would write the valence electronic configuration for this, or simply if I would write electronic configuration from the knowledge of 9th 10th class, that helium is 2, neon can be written as 2 8, argon can be written as 2 8 8. And if onto the advanced level, if I would say from the quantum mechanics, or uh, the configuration which you have learned, 1s2, this is 1s2, 2s2, 2p6, and this is 1s2, 2s2, 2p6, 3s2, 3p6. So 3p6, wherever in the this way of writing electronic configuration, wherever you get to see p6 coming, that p6 configuration, the valence electron, if it is p6, this would belong to noble gas. So make it a point. So the point here is that every element want to acquire the noble gas configuration, either by losing or gaining electron, or by sharing electrons. Just like in this case, if I would say, now we have to speak about, if in case you don't remember or don't know, Lewis dot electron structure, or Lewis electron dot structure, whichever way you want to speak it. So basically in this, we just would write the valence electron. Just like hydrogen is having one electron, that is the valence electron. Helium is having two electrons, we can write it like this. Now if I have to write for the carbon's configuration is 2 4, because the atomic number is 6, and that for nitrogen is 2 7, 2 5, and that for oxygen is 2 6. So if I just would write the valence configuration here, so how do I write the valence configuration of carbon in terms of Lewis dot structure? 1 2 3 4. These four dots which we have shown is the valence electrons of the carbon, and this way of representation is called as Lewis dot structure. And similarly, if I would write for the nitrogen, nitrogen is having how many electrons? Valence 5 electrons. So 5 electrons can be written it like this: 1, 2, 3, 4, 5, or it is your wish, you can write it like this also. Now this is at your level, whichever you want to write, you can write according. Very soon we will be seeing that which would be the right way of writing it. So if in case I write for the oxygen, oxygen is having 6 valence electron, that can be written at like this: 1, 2, 3, 4, 5, 6, or you may also write it like this: 1, 2, 3, 4, 5, 6. So this is the way it is to be written in terms of the Lewis dot structure. Now let me talk about the covalent bonding. Just like if you just define the hydrogen molecule. So as I said few minutes back, hydrogen is having one electron. This hydrogen is also having one electron. So they come close to each other. They mutually share this electron. This want to take one electron from this side. This want to take one electron from this side, so that their duplet get completed. So when you talk about hydrogen, it only want one electron more that to get the configuration of helium. So that we will say it as duplet. And if in case I write it from the fluorine viewpoint, fluorine is having how many electrons? Fluorine's atomic number is 9, so that is 2, 7. So 7 is the valence electron. Now these valence electron can be written at like this: 1, 2, 3, 4, 5, 6, 7. Another fluorine: 1, 2, 3, 4, 5, 6, 7. So this is the way we have to write: 1, 2, 3, 4, 5, 6, 7. So this seventh electron, which is unpaired, would want to take one electron from this side. And similarly, to get the noble gas configuration by acquiring the atomic number 8. And another way to write the same thing is that this also would want to take 8 electrons. So in this process, what we are able to say here is that fluorine, there is a single covalent bond. And similarly, for this hydrogen as well, you would say a single covalent bond. In the single covalent bond, one electron comes from this side, another from this side. Similarly, one electron came from this side, another electron came from this side. And whatever electrons are left here, these electrons would be said as lone pair. These would be said as lone pair of electrons. And as a matter of fact, this would be called as bond pair. In running language, we used to say in chemistry bond pair as BP and lone pair as LP, lone pair and bond pair. Is it okay? Now the point here is what we have learned out of this, that hydrogen always would want to take one electron from someone. Similarly, fluorine also would want one electron from someone because it is 2, 7. It only would want one electron so that its configuration would become 8 and the noble gas configuration is achieved. Similarly, hydrogen also is having one electron. The configuration of hydrogen is 1. It only would want one more electron. So in that sense, we will be saying hydrogen and fluorine to be monovalent elements. We will be saying these as to be monovalent elements. What are monovalent elements? Monovalent elements are those which are in search of only one electron. If one electron is being given by somebody, they tend to acquire a noble gas configuration. But here, in the case of fluorine, it just would want one more electron so that its 8 electrons got completed. So in that sense, we will be saying that it is obeying octet rule. What is octet rule? Octet means 8 electrons around the central atom. If 8 electrons are being achieved, then we will be saying it is having a octet completed. Similarly, if I would go further for oxygen now if in case I just would write for the oxygen's atomic number is 8, that is 2, 6. So how many more electrons do it want? It would want 2 more electrons to achieve the configuration 8. And 2 plus 8 becomes the configuration of neon. Neon is 10. That is what the requirement for oxygen is. So oxygen now is having how many electrons? 1, 2, 3, 4, 5, 6. Second oxygen also do have 6 electrons: 1, 2, 3, 4, 5, 6. So if in case this oxygen, which I am marking it with blue, takes 2 electrons of this another oxygen, its 8 electrons got completed. And similarly, this also would want to take 2 electrons from the other one. As a consequence, now I can write it like this, that there is two bonds created, and these two bonds then can be referred to as double covalent bond. So these are the two electrons which we have marked it like this, and these are the two electrons which I just have wrote it like this. So in totality, you would have now with you these as your lone pairs. These are your lone pairs, and these two electrons would correspond to bond pair. So in totality, we will be saying oxygen always in a search of two more electrons to complete its octet. In that sense, we will be saying it is to be a divalent entity. What is divalent entity? Divalent entity is the one, or divalent element is the one which is in search of sharing of two electrons. If two electrons it would achieve, it octet got completed. Just let me write one more example, just like in the case of water. So if in case of water, I just would write oxygen is having how many electron, how many valence electron do it have? It is having 1, 2, 3, 4, 5, 6. How many electrons more do it want? It would want two more electrons, and that two electrons can come from the hydrogen. So this hydrogen would give one electron. This hydrogen also from this side would give one electron. In the process, duplet of hydrogen got completed. It acquires a noble gas configuration of helium, and that of oxygen also got completed, because now around oxygen there are 8 electrons. Out of these 8 electrons, 2 are bond pair and 2 lone pairs. So in that sense, now water can be written like this. So in this form of representation, you would see these are the two lone pairs which we have achieved, and there are two bond pairs around the oxygen. So oxygen in a process, I do write once more that oxygen is a divalent entity. So it always would want two more electrons to complete its octet. So I think this point is also clear to all of you. Now, similarly, if I would go for nitrogen, atomic number of nitrogen is 7. That is, configuration is 2, 5. It is in search of 3 more electrons. If 3 more electrons it would get, it would achieve the configuration of, individual nitrogen atom would achieve the configuration of uh, uh, neon. That's atomic number is 10. So in that sense, if I would write nitrogen is having 5 valence electron, the next nitrogen also do have 5 electrons. So if in this particular nitrogen would take 3 electrons of this nitrogen, its octet got completed. And similarly, if it would take from this side also, its octet get completed. Both would have 8 electrons. So that 8 electrons can be shown it like this. Now this is called as triple covalent bond. Triple covalent bond. So one line which is in between two atoms, this line which we have shown, this is single covalent bond. If I make it 2, it is double covalent bond. If I would make it 3, it would become triple covalent bond. So in that sense, nitrogen always is in the search of three electrons, and 3 electrons it can get from the other nitrogen, or if in case I just would write ammonia, NH3. So here the nitrogen is having 5 valence electrons, 1, 2, 3, 4, 5. I deliberately wrote it like this because nitrogen is getting its electron from the 3 hydrogen atom. 3 hydrogen atom also is in the search of 1 electron. So 1 electron these hydrogens would give to the nitrogen. In the process, their duplet got completed. And parallelly, what has happened, that around nitrogen you are able to see there are 8 electrons achieved, and this particular is called as lone pair, and these would be said as bond pairs. So this is the what I would say it in the way that it is the simplest of way of discussing what basically is the covalent bonding. That is because of the sharing of electrons. Now coming on to the carbon. So this is the one which we wanted to address with, because this is the one which actually would make the entire of your organic chemistry. Now, carbon atomic number is 6, configuration is 2, 4. So it is in search of 4 more electrons. If 4 more electrons got shared with this particular carbon, it happens to get the configuration 8, and again it would achieve the configuration of neon. Just like if I would write CH4. So in the case of CH4, carbon is having 4 electrons, very simple it is. And if I just would make one electron, if I would give by if hydrogen would share one electron with carbon, so in the process the duplet of hydrogen got completed, and along with it the 8 electrons, the octet of carbon also got completed. So we shall be saying very soon that carbon is tetravalent. It always is in the search of 4 electrons, and if 4 electrons it do get by sharing, we would be saying its octet got completed. Now let me cut short the long story short in a way that let us make it more simple, that we basically would be requiring in this particular session or in the upcoming 4, 5 or 7 session, onto the elementary part, that uh, basically we would be saying it this way, that hydrogen and fluorine are monovalent. This is the one electron of hydrogen, this is the one electron of fluorine, which is unpaired. Now this fluorine is in search of one more electrons, and if somebody else would give this one more electron, I would be saying this is to be monovalent. And similarly, hydrogen would want to achieve the configuration of helium by taking one electron from somebody. So this, in a way, we will be saying hydrogen and fluorine at this point of time is monovalent. And one more thing which I would address here only, that fluorine and hydrogen are always terminal atoms. They always get joined at the terminal. They never would become the central atom. They always would join to the central atom. What does it mean? As we do some problems, you are able to understand it. Now coming on to the oxygen. So if I would write the electronic arrangement of oxygen, the electronic arrangement of oxygen is somewhat like this. So here you have 6 electrons of oxygen. Oxygen is in search of 2 more electrons. So 2 more electrons it can get from someone. So if it takes 2 electrons in this way, the way I have shown, I will be saying this oxygen is making double covalent bond. These two lines would be shown for the double covalent bond. But parallelly, it may take it like this also, that if I show the bonds like this, then what does it mean? That oxygen is having 6 electrons and they are taking one electron through the single covalent bond. So in that sense, we will be saying it is a divalent species. It is divalent. Divalent in what sense? That oxygen would join with someone either through double bond or through two single covalent bonds, either through double bond or through single covalent bond, two single covalent bonds. And when it is joining with somebody through double covalent bond, then it tend to become a terminal atom. And when it is joining with someone from both sides, then it is non-terminal. Non-terminal means which is not at the corner. This would be at the corner, but this would not be at the corner. Is it okay? So this is the another statement which you always have to keep it in your mind. Now coming on to the nitrogen. So what is the state of affair of nitrogen? Nitrogen is having how many electrons? 7. 5 are the valence electrons. So 5 valence electron, I can share it like this. The way we have just shown the triple covalent bond, 1, 2, 3, 4, 5, and in the process it can take 3 electrons from someone, and this particular thing would be said as triple covalent bond. This would be said as triple covalent bond. So all of this would come with the practice, and more you practice, as I always say in the organic chemistry, more you practice, more you learn. So this may also join with somebody like this also. One from the double bond, 1, 2, 3, 4, 5. Still this is having a lone pair, one lone pair. This was having two lone pairs, and here also it is having two lone pairs. One is this, another is this. There are two lone pairs on oxygen. And now just see here, nitrogen can take 3 electrons this way, one from the single bond and two from the double bond, and still it would have 8 electrons around it, and one still would have the lone pair. or it can join by 3 single covalent bonds. If you show it by 3 single covalent bonds, 1, 2, 3, 4, 5, still it is having one lone pair. And wow, this is very interesting. So nitrogen then can be said as to be trivalent. Obviously, when it is going to join somebody with a triple covalent bond, then it would behave like a terminal atom. When it is combining like this in the center, from one side single bond, another side double bond, or from the three sides it is having single covalent bonds, then it would be behaving like a non-terminal atom. So the bonding arrangement should be clear to all of you. So this I think is very clear to everyone. Now let me place one more here. Oh, what happened? Just hold on for a while. I just have done the mistake. Okay. Now where we were, now coming on to the topic of carbon. So the next is the carbon. When you talk of carbon, what basically we can bring here? Carbon we may say to be tetravalent. So carbon is tetravalent species. Now what does it mean? This tetravalency or tetravalent entity make it a such a beautiful compound that you would get to see lot of organic compounds. Let me first complete it and then we'll explain. Now carbon can join by because carbon is having carbon is 6 and it is 2 4, it is having 4 valence electron. It just would want 4 electrons to be shared with it. So these 4 electrons can be shaded like this. These are the 4 valence electrons of the carbon, and this can come from this side, 4 sharing. One way is this. Second way is it can also do it like this, that these are the 4 electrons and there is no lone pair. These are the 4 electrons and these 4 electrons can be shaded like this also. And another way is that if you just would write it like this, two double bonds on both sides. So these are the 4 electrons, and if in case I just would say the two electrons would come from somebody, so it becomes 4. Or in a way you could also show it like this also, that these are the 4 electrons of the carbon and these 4 electrons can join it like this. Is it okay? So in a way what I'm trying to say here is carbon can make 4 types of bonding structures, bonding formation. It can be made with the carbon in a 4 ways. 1, 4 single covalent bonds, 1 double, 2 single, 2 double on both side, 1 single and 1 triple. So this in a way make it a tetravalent. So another thing which you always would see, that in the case of the carbon, because carbon would always come in the center and something is going to attach with it to complete its covalency. So it would always be a non-terminal type of a atom. So the terminal one can be hydrogen. Oxygen can also be terminal, but if it is joined through a double bond. And nitrogen can also be a terminal when it is joined with a triple bond. Now here comes the question that carbon would never be a sort of terminal atom. It always would join in somewhere in the somewhere inside the molecule, not at the corners. So as we do some problems, we are able to understand it well. So let me say it once again to all of you. What we have learned out of this, we just have learned one thing, that the point you have to keep it in mind is that we learned one thing, that hydrogen and fluorine are monovalent, oxygen is divalent. Let me write it once more for you, just for your understanding what we have just said. We said it like this, that hydrogen always join with a single bond, fluorine with a single bond. Oxygen can join either by 2 single covalent bonds or with 1 double bond. And nitrogen can join with someone by 3 single bonds, 1 double, 1 single, or 1 triple. And lastly, the carbon would always join through someone by 4 covalent bonds, or 1 double, 2, or 2 double, or on one side 1 triple and 1 single. Here many times people ask me this question, that in case of carbon, why can't you write it like 4 bonds? This is not possible. Why is it not possible? for which you have to go into the valence bond theory from the chemical bonding chapter. So at this point of time, you just rule out it. This would not happen. Okay. So now coming on to the another point. When some charge is present on carbon, nitrogen, or oxygen, or some other heteroatom, so what is to be then seen into? When carbon is containing a positive charge, just like if I would say that if I just would write, let's say I just would take an example of methane. And in this methane, these are the electrons of the carbon, valence electrons of the carbon, and these cross electrons are of the hydrogen. Now, due to some reason, if in case with some superpower energy, I just have broke this bond like this is called as heterolytic cleavage. Lytic means or lysis means killing. Hetero means not from the center. If I would break it like this, what I do get here? I would get a structure somewhat like this, isn't it? So this dot electron, this dot which this red dot or pink dot which was of carbon now is with the hydrogen. So this hydrogen would get a negative charge because it got an extra electron. And as a matter of fact, what is the state of affair of the carbon? One of the electron of the carbon, this electron of the carbon, this particular electron of the carbon has gone to the hydrogen. So this in a way now is feeling one positive charge because one electron of the carbon went to the hydrogen. And as a consequence, we would be writing here, these are the electrons of the hydrogen. So I just would write something like this we have achieved. So carbon carries a positive charge. Now, as a matter of fact, this would be dealt in very detail in the upcoming sessions of general organic chemistry. This, whenever carbon carries a positive charge, we generally speak it like this. This is carbocation or carbonium ion. Carbonium ion. Always remember it like this. When carbon is carrying a positive charge, its tetravalency would not be there. Then around a carbon, there would be three bonds. There would be three bonds. This you always have to keep it in mind. And as a matter of fact, if I similarly do for nitrogen and other species, for the other species also, if I just would write it for the other species, if just hold on, if I just would write for the nitrogen, nitrogen is somewhat like this. If I would say ammonia, as a matter of fact. Now, in the case of nitrogen, there is a lone pair. There is a lone pair. And here, if I would bring one H positive, so this lone pair can be given to the hydrogen. So in the process, what you would achieve here is that you did this thing. So these are the electrons of the nitrogen. Now this has gone to the H positive. H positive did not have any electrons for the bond formation. So now there is a bond formation happened with the hydrogen. So since it has happened with the hydrogen, so I may write it like this. So these two electrons now got formed a bond with the hydrogen. As a consequence, this nitrogen would get a one positive charge. What I'm trying to say to you is that this sort of a species is being formed, and these two electrons which we have shown, these two electrons are actually of the nitrogen, but one of the electron has gone to the hydrogen now. So as a consequence, this would get a positive charge. Always remember, when the reactant, overall reactant is having one positive charge, product would carry one positive charge. So nitrogen when get a positive charge, it would get a positive charge when its lone pair get consumed up somewhere. So then it would get a one positive charge. Now this always you have to keep it in mind. Now here I do want to share with you one more thing, that if in case here we spoke about octet rule, that the every element would want to achieve the noble gas configuration. But this is an old method. In the latest method, when you do in the chemical bonding in the valence bond theory, there are many molecules which are existing in the nature and they are not obeying the octet rule. Just like an example, if I would write Be2F, beryllium fluoride. So don't do it that way. Don't say it like this, or don't feel it like this, that this molecule would not exist, because beryllium atomic number is 4, valence configuration is 2 2. Now it is also having 2 electrons. So beryllium is having 2 valence electrons, and fluorine is having, all of you know fluorine is 9, that is 2 7. So fluorine is having 7 electrons, 1 2 3 4 5 6 and 7. And similarly on this side also fluorine is having 7 electrons. As I said to all of you that this particular chapter of chemical bonding is a lengthy one. I am just placing few things in concrete which is required for the organic. So make it a point here. I just want to say it here is that although its octet got completed, but the octet of beryllium is not getting completed because it is around beryllium. There are only 4 electrons. It still would want 4 more electrons to complete its octet to get the noble gas configuration. But as a matter of fact, it is still existing in nature. BeF2 still exists in nature. So make it a point. BeF2 exists in nature. And similarly, if I would say for BF3 is also existing in nature. Beryllium, boron's atomic number is 5, that is 2 3, and it can make 3 bonds with the fluorine. And as a matter of fact, here you have 3 electrons of boron, and these cross electrons are of fluorine. So fluorine's octet got completed, but that of boron did not happen, but still it exists, although it is not obeying octet rule. And there are some compounds of the third period which you would later on see that in them, the around central atom, the electrons can be more than 8 as well. They can be more than octet, just like if I would write PF5. So in the case of PF5, you would see that there are 5 fluorine atoms getting attached with it, and as a consequence, because phosphorus is having 15 electrons which can be written as 285, and still it is quite a stable compound. And around phosphorus there are 5 valence electrons, and 5 of this fluorine atoms joins it like this. As a consequence, you would get to see a PF5 being formed, although around phosphorus there are 10 electrons. And similarly, from sulfur and chlorine, they may also can make their octet greater than 8. So they do exist in nature, but that we will be discussing in the topic of chemical bonding. Let me state what we have just said. Basically, in the organic viewpoint for upcoming 4-5 sessions, what is the basic requirement I would be requiring? I shall be requiring this particular discussion, that this is monovalent, this is divalent, this is trivalent, this is tetravalent. If you are able to remember or understand this one, it is more than sufficient. And along with it, I just do add few things more, that whenever I speak of covalent bond, because this again from the chapter of chemical bonding, there are 2 types of covalent bonds which we would not be discussing in length. Somewhere after IUPAC naming, advanced level of chemical bonding I will place in the organic sessions. So here you just remember this is referred as like sigma bond, and this is said as pi bond. Now make it a point, whenever around the central atom, just like if this you have a carbon, you only have single bonds. All these single bonds would be said as sigma bonds. These are said as sigma covalent bonds. And when you write something like this, there is a or you may write it like this, that around carbon or for any element, because 2 elements when combined with each other through covalent bonding, sigma bond always has to form. And once the sigma bond has happened, then there is chances pi bonding formation can happen or may not happen. That is another domain. But at this point of time, you have to understand that if around carbon there are 2. So if I would say, how do I define what is pi bond? There are 2 sigma bonds and there are 2 pi bonds. So, and here also these are 2 pi bonds, and this one is sigma, this one is sigma. So make it a point, when you write between 2 covalently bonded atoms, if you write like this, AA, so this would be sigma. If I would say something like this, AB, so out of this, one is sigma, one is pi. And similarly, if I write between AB, there is triple bond, then you may say there is 1 sigma, and there are 2 pi bonds. So this you always have to remember. So if I just would say here that around this carbon, there are 4 sigma bonds, 0 pi bonds. There is no pi bond. Pi bond would be seen whenever you have something like this or this. If this representation is there, then this means there is 1 sigma and 1 pi. Here is 1 sigma, 2 pi. Is it okay? So if you have this sort of a structure, so here I would say these all are sigma, these are all sigma, and this is sigma, 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 and this is 1 pi, and this is sigma, and this is pi, pi, and this is sigma, and here also 2 are pi and 2 are sigma. So we will be saying here you have 2 sigma bonds and 2 pi bonds. Here we will be saying 3 sigma and 1 pi bond. And just don't get disheartened with this thing that around a carbon, if there are only sigma bonds, we will be saying it is sp3 hybridized. This we will be discussing in detail in the advanced level of chemical bonding after 5-7 lectures. And here we will be saying it has to be sp2. sp2 carbon must have 1 pi bond. sp2 carbon must have 1 pi bond. And when you talk of 2 pi bonds, then that particular carbon has a hybridization which we say it as sp. Because those who are from the 9th, 10th and 11th base, those who have just started, they may feel little upset with this what sir is writing, but those who have already done 11th class, they will feel the viewpoint that what basically sir is representing in terms of hybridization. So if around there is carbon there, now let me say it once more just to conclude the thing, and then we'll go into a very interesting domain of covalent bonding. Now, what we can say that if around a carbon there are only single bonds, then we will be saying four single bonds means it is having 4 sigma bonds, and there is no pi bond. There is no pi bond. There is no pi bond, and this carbon, if is being shown it like this, we will be saying it is having 3 sigma bonds and 1 pi bond. And if I show it like this, I shall be saying this to have 2 sigma, 2 pi. And in the process, I may also say this is sp3, this carbon is sp3, this carbon is sp3, this carbon is sp2, and this carbon is sp. So this always you always have to remember. Now the coming on to the point that if now I would provide you with some formula, say for example, now this is where the interesting aspect of this topic would come into picture. Now if I would say that I shall be giving you some compound of this type C2H6, say for example, or for that matter if I just would write C3H6 or C 4H6, something like this, or C6H6, for which I shown you last time in the introductory lecture that C6H6 have the combinations almost around more than 217 structures can be possible with this 12 atoms. So that is very interesting. That is where we would be soon addressing it, that carbon is having a unique property of showing lot of compounds. Now the point here is that how do we get to know? In today's session I am placing some fact and figure. In the next session also I am going to give you something very interesting by which you would be able to see that a given molecular formula of organic compound can be represented in many forms. Now the point is that how do we say that how many, if I would say for any stable structure with even number of electrons, any stable structure having even number of electrons, if you just would want to find out the number of covalent bonds, if you just would want to find out the number of covalent bonds, now what is the way? So this formula I designed that few years back. So number of covalent bonds is, we will say it is like this: electron demand, what is it, electron demand, and electron supply. How many electrons are there in the valence shell of a given element, and how many electrons do it want to complete its octet. So what is electron demand? Electron demand of an element is the number of electrons it do want to have the noble gas configuration, and electron supply is the actual number of electrons it is possessing in its valence shell, and that is what you call it as electron supply. Divided by 2, you would get the number of covalent bonds. Now the point here is, just like if in this particular formula we would be mostly using in terms of the organic molecules. So here, to begin with, wherever some other things would come into picture, I will pass it through the problem solving. So for hydrogen, the electron demand is always 2, because hydrogen is having one electron and it is always in a search of one more electron. So the demand is of 2 electrons, so total electrons it would want is 2 to have a helium configuration. And for all other elements which we are using in the organic chemistry, carbon, oxygen, fluorine, nitrogen, sulfur, phosphorus, for all of them we will be saying the electron demand is 8, because the valence shell, just like for the carbon, the electron demand is of 4 electrons. So in totality it want 8 electrons, isn't it? Because its atomic number is 6, 2, 4 is the configuration. It would want 4 more electrons. So the electron demand is of 8 electrons. Is it okay? So in other words, what we are trying to say is electron demand is the number of electrons it would want to achieve the nearest noble gas configuration. So hydrogen would want one more, so it is total 2. And if we talk about carbon, or that matter nitrogen or oxygen, all of these would want in the valence shell of their 8 electrons. So the electron demand is of 8. Let me do the problem solving and then you would get to understand what I'm trying to say. Just like if I just put start with the carbon, CH4. One way is, which you, now it is at your discretion, I am telling you 2-3 ways. Whichever way you feel comfortable with, you can go with that. One way is, you have a carbon and 4 hydrogen atom. You just would see it like this, that carbon would be the central atom because it always would be the central atom, and hydrogen is always monovalent. So hydrogen would always join with someone only through a single bond. So there are 4 hydrogens, so you just have joined it with 4 single bonds. So this is one way of discussing the thing. So I just have took something from here. So I just have taken this entity from the carbon side, and from the hydrogen side I just have picked this one. This one I picked from the hydrogen. So this way you happen to get that particular structure. Now, if you just would want to do, because this is a simple one, we can address it this way. When the things would become complex, you would require the assistance of this formula. Now, what we are saying is that carbon is 1, and what is the electron demand? 8. So, and what is the hydrogen? Hydrogen are 4. How many electrons hydrogen would want? 2. So it is 8. So total demand is of 16. 16 electrons are required. And what is the electron supply? There is one carbon which is having 4 valence electron, and there are 4 hydrogen atoms which is containing 1 electron, so it is 4. So 16 minus 8 divided by 2, so it becomes 4. So there are number of covalent bonds are 4. So in CH4 there are 4 covalent bonds. So that is quite evident. These are 4 CH. There are 4 carbon hydrogen bonds. Similarly, if I move further, C2H6. Now this is very interesting. C2H6. Now C2H6, how many carbon atoms do I have? 2 carbon atoms. And what number of electrons they actually would want? 8. So the total becomes 16. Here, how many electrons one hydrogen atom want? 2 electrons it would want. So it is 12. So in totality, this becomes 8, 28. And as a matter of fact, for the electron supply, how many electron supply? One carbon is giving me 4. So this is 8, and this is giving me 1. This is 6. So this becomes 14. So this would turn up to 7. So there must be 7 bonds in C2H6. One way of doing is this. Another way, which I already have spoken about, because whenever you have a molecule having more than one carbon atom along with the hydrogen has to join from the terminals, from the corners. So carbon-carbon bond must be there. So I can say it like this. This must be joined to each other through the carbon-carbon bond. And now the fact of the matter is how many hydrogens you want to join is 6. So to complete its tetravalency, you have to place 4 bonds around this. Because hydrogen only would join with the single bonds. So how many bonds you would get? 7 bonds. 7 covalent bonds you have achieved. And all of these 7 bonds are sigma bonds. This is also sigma, sigma, and there are 7 sigma bonds we have created. So one way of doing is this one. Now going for the further one. Now if we have C2H2, now if this is the case, so the demand is 8, so this is 16, this is 2, this is 4, so this becomes 20, and the supply is 4 and this is 1, so this is 4, this is 2, so this happens to become 6. Am I right? Oh, sorry. 4 to the 8 and 10. So this is 10. So 10 by 2, this becomes 5. So there would be 5 covalent bonds in this particular entity. Now let me do it in another style as well. As I said, carbon-carbon must be joined at least by single bond, and hydrogen always join the carbon with one bond only, but this carbon still would be requiring more electrons to make its completion of electrons. So how many, because as we said, carbon can join with someone in any of these 4 structures, in any of these 4 ways it can join, nowhere less or nowhere more, unless until it is neutral. Now the point here is I just would pick something around it. So I just have picked this one, because if I just would make it this way and one bond here and one bond here, so you happen to get 5 bonds and the covalency of all the carbons also got completed. Wow, this is very interesting. Did you get this point? I hope you are. If in case I'm going little fast, you just would pause and draw it yourself and try to figure it out. Just make it in the terms of electrons also. These are the 4 electrons of this carbon and these are the 4 electrons of this carbon, and these are the electrons of the hydrogen, or you can say it like this. So the duplet of this got completed, duplet of this got completed, and 8 electrons of this got completed, and 8 electrons of this also got completed. So I think the things are very clear to you. So we may say it like this. So in a simple way, we may also say this is 1 sigma, this is also 1 sigma, this is 1 sigma, and there are 2 pi bonds here. And since around the carbon there are 2 pi bonds, this carbon would be sp hybridized, this also is sp hybridized, as a matter of fact. Now make it, let me go into the further one. So I already have calculated out, and you just, because the carbon would want 8 electrons and hydrogen would want 2. This is the demand. And what is the supply? The carbon is having 4 valence electron and hydrogen is having 1. So in this particular molecule, now please be attentive. Now in this particular molecule, you just would want 9 bonds. There should be 9 bonds, and we know for sure that carbon must have been joined with carbon at least with one bond. So there are 3 carbon atoms, you can join it like this. Now this is very interesting. And there are 3 carbon atoms, you can join it like this also, isn't it? This is, you can make it like this also. Now the point here is you have to now place the hydrogen atoms. So how many hydrogens I can place here? So if I just would place 3 hydrogen atoms here, so 3 hydrogen atoms I already have used. Now we still, because hydrogen atoms are how many? 6. So I already have used 3 hydrogen atoms. Now if I just would make 2 hydrogen atoms here also and 1 hydrogen atom here, so now I am cut short of, this bonding is not complete, because I just would want around a carbon either 4 bonds like this, or 4 bonds like this, or 4 bonds like this, or 4 bonds like this. So here what we did in the first case, I used this one, this object, this is being used around carbon. I just have taken 4 single bonds. But now this also is this is okay, but this covalency is not complete because I already have used up all the hydrogens. Now what I can do now is, a simple thing I can use here is that if I just would Remove this one. If I just remove these two hydrogens and place the double bond here, if I just would place a double bond here and one hydrogen on this side, so this way you happen to achieve the covalency of all the carbon atoms. Around carbon atoms you have four bonds. So if you could see 1, 2, 3, 4, the four bonds got completed. Around this carbon also 1, 2, 3, 4, four bonds got completed. And around this one also 1, 2, 3, 4. So you could see that around all the carbons the covalency got completed. So what basically you have taken up? One carbon you used up this one, another carbon you used this one. Both of these carbons are having one pi bond along each other. And you may also use it like this also. So here if you place two hydrogen atoms, because you have to create four bonds around the carbon, so you can place it like this also, you can place it like this also. So as a matter of fact, what we can say here is that in this particular structure, the structure which we have just shown to you is this one. What I did, that C3H6, I may say it like this, that I can make this C3H6 in two ways. One way is that I just would write it like this. Is it okay? So I can say it like this. These are the hydrogens, hydrogens, hydrogens and hydrogens, and I just have placed one double bond here. And now what you are able to see here is that or I may say it like this also. So this is beautiful. These two are the possible structures of C3H6. These would be said as, very soon we will be doing it in very detail, isomers. If you go to a market to buy this particular compound C3H6, the shopkeeper will say to you, would you be wanting propene? This particular compound is going to be said as propene when we do the IUPAC naming, and this would be said as cyclopropane. So both of these are two different entities, although their molecular formula is same. So that particular species is called as isomer. So my endeavor in upcoming 1, 2, 3, 4 more sessions, before you actually start naming them, I just want to expose you, or I just would want to share it with you, that open up your mind and make as many structures as you can. So that is where you would feel enthralled with that the organic chemistry is so interesting. From the same molecular formula, you can get with number of structures. Now, just if I would go further, and in the next session, you will find the way and means other than this one, which I am just placing it in front of you. You can do it in other style also, which we will be coming up in the next session also. Now C3H8. So in totality, if you just would do it yourself in the calculation, carbon want 8, hydrogen want 1, and this is the valence, the electron supply is of 4 for the carbon and 1 for the hydrogen. So in totality, you have 14 bonds and you have 5 carbons, and these 5 carbons must have joined to each other at least by single bonds. As a matter of fact, at least by single bonds. And now just you have to use 8 hydrogen atoms to do all the combinations. So 8, how can I do? If I just would like write it like this, these 3 hydrogen atom I placed it here, 3, 4, 5. 5 already have used, 6 I have used, this is 7 hydrogen atoms I already have used up. And in all of these usage, what also I have seen is that this carbon is tetravalent, 4 bonds around there, 4 bonds around there, 4 bonds around there. So already I have used 8 hydrogen atoms. 8 hydrogen atoms I already have used. 7 hydrogen atoms I already have used. I have to use one more hydrogen atom. If I would use one hydrogen atom here, I'm able to see that the covalency of this particular carbon is not completed, nor is being completed by this carbon. So what I can do? So here you have to apply a bit of mind. So if I would place hydrogen here and just would place triple bond in between, here if I would place triple bond, now you could see around every carbon you actually have achieved the covalency, tetravalency has been achieved. So this particular thing you always have to keep it in mind. So this is the way. Now let me count. Is it 14? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Wow. So this means this formula is perfectly working with this entity also. But here is a very important thing which you always have to remember it. In the next session also I will speak on that part, is that is bond line representation. Bond line representation. This we will do in the next class also, and in the subsequent 4-5 sessions also we will be doing it in detail. So this bond line representation, what does it mean? So these are the 5 carbon atoms, 1, 2, 3, 4, 5. You can place these 5 carbon atoms like dots. 1, 2, 3, 4 and 5. So I just have placed these dots, these corners as to be the carbon. There is no need of writing in this representation of the hydrogens, and just would place a triple bond here. So in simpler way, we may represent this particular entire molecule in this fashion also. Now let us do one more thing with this. We have C5H8. In the next session we will be discussing this particular molecule in quite a length. Now you just have wrote it like this. If you could recall, you created a triple bond here, but somebody else can also write it like this also. Someone else can also write it like this also. He or she just would place a double bond here or double bond here, or somebody else can write it like this also. This makes the chapter, this makes the things very interesting, that a double bond here, or someone else can also write it like this also. This is beautiful, and I let you know next time that how you can address this particular thing. Now if I just would place it here, 3 hydrogens were here, 2 hydrogens were here, 2 hydrogens were here, 1 hydrogen here. So in the process all the covalency, tetravalency has been achieved. But here this is CH3, this is CH2, and this is CH3. Still it is 8. 3 and 3, 6 and 2, 8. And the around every carbon tetravalency is still maintained. Here 1, 2, 2 bonds are already there. So you are going to place 2 hydrogens here. 1, 2, 3, one more hydrogen can be attached here. 1, 2, 3, one hydrogen can be attached here. One hydrogen can be attached here. 3 hydrogens can be attached here. So in the process, you are able to see 3, 3, 4, 5, 6, 7 and 8. Still it is 8. And similarly, if you just would place here 2, and this also is the same one. And similarly, if I just would place a double bond here, and now just would place all the hydrogen atoms around it. So this is 1, 2, 3 bonds are already there. So 1 hydrogen can be attached here. 1, 2, 3, 1 can be attached here. And now you could see 1, 2 and 2 hydrogens can be attached here, 2 hydrogens can be attached here, 2 hydrogens can be attached here. So this particular entity would be having lot of isomers. So this in a way makes the subject very interesting, that simple molecule can can be obtained in this fashion, or this fashion, or this fashion. So there are still many number of structural things, structural isomers possible for this formula. And subsequently, we then would want to learn that if all of these structures are there in front of you, what are their names? How do you name them? So my endeavor is first let you know that how you could get the different structures, because that would open up your mind in regard to the organic, and then we will address what are these function groups, what are the names of these. So in upcoming 4-5 sessions, first endeavor of us would to know that if you have any organic entity, in how many ways you can draw that structure, and then we'll see what function group it is having, what is the name of that all that things we will do in the next in the subsequent lectures. Similarly, if I would proceed further, now let me bring in one more. I brought oxygen into it. So oxygen again is 1, and it would want 8 electrons, and the valence electron it is having 6. The valence electron for the oxygen is 6. So the electron supply is 6, and it is requiring 8 electrons to have the noble gas configuration. So if you do the calculations, this comes out to be 8. So 8 covalent bonds are there in this formula. Now the point here is that this C2, so there can be like this, there are two carbon atoms, and you know for sure that oxygen either can join with double bond or with single bond. So in this lecture, in the coming lecture, in the next lecture, we will address that with the formula only you are able to see that would it be joining it by this or this in the subsequent lecture, but not today. So here, if I have to place the oxygen, I just have placed oxygen like this. Is it okay? Now, if I just would do the combination in terms of the hydrogen, so how many hydrogens do I get? So here you have 3, here you have 2, and one hydrogen can join here. So this is what you call it as ethanol, by the way, and this can also be written as CH3 CH2OH. You can show it like this, but someone else, any of you can draw it like this also, because oxygen can join with single bonds like this also, both carbon on each other sides. So here, if you have to place the hydrogens, so here you have 3 hydrogens because oxygen's covalency is being achieved, and here also you have 3 hydrogens. So in a way, what I'm trying to say here is that this particular entity which we have just wrote, C2H6O, this can be written in this fashion also. This can be written in this fashion also, or in this fashion also. That if you write it like this also, there are two possibilities of it. And these condensed formula for this can be written as CH3 CH2OH, and this may be written as CH3O CH3. So this is called as alcohol. Later on we will see, and this is, we call it as ether. Function of it is ether. So these two are called as isomer. So this is the beauty of the thing, that if you have with you a molecular formula using this style of formula, where electron demand minus electron supply divided by 2, you would get with a number of covalent bonds. And once you get the number of covalent bonds, in the next session I also would let you that from the formula you also would get to see that in that formula how many double triple bond can be possible, or if that formula is only having single bonds, or double or triple can also be possible. That we will do in the subsequent lecture. And similarly, if you go for this one also, so this is your homework. Try to make all possible forms of this particular representation, and you would feel little enthralled with that. If you have with you C2H3N, draw all possible structures for it. So let me state it once more to all of you that principally the objective of today's session is to tell you that these are the terminal atoms. This would be monovalent. If you have learned this much, many of the things of the organic chemistry we can easily handle with. And this is trivalent, and carbon always would be tetravalent. Around the carbon there would be 4 bonds, 4 single bonds, or 2 single, 1 double, 1 triple, 1 single, or 2 double bonds. And when it is single bonds, the single bonds would be either joining with carbon or hydrogen, and double bond can be, okay, let me show it to you once more. So if you have CH4O, so which way you should write it like this, because we know for sure carbon is supposed to getting attached with the hydrogen only, because hydrogen always join with a single bond with a non-terminal atom. Now you are left with one oxygen, and oxygen joins either by this or by this. If I would join it like this, one bond of the hydrogen I can join it like this. Here I haven't used the number of covalent bonds, simply with the viewpoint of this formula. So I picked one carbon this way. With this I just have attached this oxygen and this much hydrogen. So these 3 selections I have done for this particular formula. Similarly, if I write CH2O, so the carbon is still there. Whatever hydrogens are there, I just have joined with the carbon, and I still would left with one oxygen. So oxygen can join it with double bond. So here you are able to see that simply we just have done a simple understanding. I just have picked this oxygen this carbon and this hydrogen. Are you able to get this? This is the main objective of today's session. So this would come with the practice. Now again you have done one thing. So here you have a carbon and two oxygen atoms. So if I just would attach with this carbon two hydrogens, and what I'm now left with is oxygen. So there are how many oxygen do I have with me? So the oxygen I do have is two oxygen atom. So two oxygen atom either can join, if I join it like this, one oxygen still is left pending. So I can join it like this, but then I'm left with one hydrogen. So there is no hydrogen here. So if I just would remove hydrogen and bring it here, then this carbon would not remain tetravalent. So I have to do a bit of homework or bit of work to get with an answer. So I can do it like this. If you do it like this, you would get with the answer, isn't it? So you have two hydrogen atoms, two oxygen atoms and one carbon, and the covalency of all of these got completed. Around carbon you have four bonds, 1 2 3 4. Around oxygen you have two bonds, 1 2, and around hydrogen there is single bond. That is fair enough. And similarly if you go for this one, so here you have carbon must be joining with nitrogen and the hydrogen must be joining with the carbon. So this is the simple trick you always have to play with. So here what I did is I just have picked this nitrogen all with the single bonds, carbon with all the single bonds, and hydrogen. Now next time what we are going to say state here is that we will be doing a lot of practice next time, and then would let you know that which way we will make the things more interesting and easy for you. In the next session we will be going to address the fact here is that if you are being given some formula, if I just would give you just like this formula, so could you be able to tell me that how many pi bonds are there in this, how many double or triple bonds are there in this? That understanding if you would get, then the formulation or the making of the structure even would become more easier. And one more thing I should add here is that if around a carbon there are single bonds, we will be saying it is saturated hydrocarbon. And if around a carbon there is double bond or a triple bond or two double bond, these also is referred to as multiple bonds. And then we will be saying it has to be unsaturated hydrocarbon. Unsaturated hydrocarbon. So multiple bonds are the bonds where you tend to see carbon making double or triple bond. It is not only with the carbon. If I just would write it like this, carbon can make multiple bonds or double or triple bond with oxygen. It can make multiple bonds with nitrogen as well, CH3C triple bond in cyanide. So all of these formulations we will, so the goal of this sessions would be, upcoming 2-3 sessions would be, first, if you are being given a molecular formula, from that molecular formula if you are able to make lot of different compounds, keeping the octet complete, keeping the Lewis structure, by making the bona fide Lewis dot structure, then in a way you are able to see that so beautiful is the organic chemistry. And then the next step would be, if you have made all these different structures for the same formula, then we would go for the learning of the functional groups. What is the name given for that particular group or that particular molecule? So hope you have enjoyed today's session, and we would be seeing you once again in the next session. Although this video has become a little lengthy, but in a way, for a starter student or the student who has just started the organic chemistry, he would feel very comfortable with. So hope to see you in the next session, where we will be doing very interesting topic in the next session. Bye bye, take care, take good care of yourself.